Hello, Enjoy Swaminarayan to all. Today, for standard 12th science in physics subject, we are going to continue our chapter 3, current electricity. The topics that we are going to cover are 3.10, combination of resistors, series and parallel, 3.11, cells, EMF and internal resistance, and 3.12, cells in series and in parallel. So let's start with our first topic, which is topic 3.10, combination of resistors, series and parallel. The current through a single resistor R across which there is a potential difference V, it is given by Ohm's law I is equals to V by R. Means the current that is flowing through a resistor R across which there is also a potential difference V, and it is given by Ohm's law I is equals to V divided by R, that you have already seen in previous topics. Resistors are sometimes joined together and there are simple rules for calculation of equivalent resistance of such combination. Means this resistor can also be joined with together, and there are also some simple rules that are used for calculating the equivalent resistance in this combination of two or more resistors. When two resistors are said to be in series if only one of their endpoints is joined, as shown in figure 3.13. Means two resistors are said to be connected in a series format if only one of their endpoints is joined with each other. Means one endpoint of both resistor is joined with other resistor. If a third resistor is joined within this series combination of two, as shown in figure 3.14, then all the three are said to be in series. Means if we join one resistor with other resistor, the end point of one resistor will be connected to the starting point of another resistor, and similarly if we join third resistor, it will be in the same format. So when we connect these resistors in this format with each other, then it is said that the resistors are combined in a form of series, and clearly we can extend this definition to series combination of any number of resistors. Mean you can add any number of resistors in this series, you have to just combine this resistor by connecting their endpoints. Two resistors are said to be in a parallel format if one end of all the resistor is joined together and similarly the other ends are joined together. Means we can say that two resistors are combined in a parallel format if we connect the end point of one resistor with both the endpoints of another resistor. As you can see in figure 3.15, the both the endpoints of both the resistor are connected with both resistor. Means one endpoint of one resistor is connected to another resistor, and the another endpoint of the resistor 1 is connected to resistor 2. Means both the endpoints of both resistor are connected to each other, is said to be that two or more resistors are combined in a parallel format. Consider two resistors R1 and R2. As you can see in figure 3.15, consider two resistors R1 and R2. The charge which leaves R1 must be entering R2. Means as we are connecting the resistors in this parallel format, then the charge that leaves R1, means when the charge leaves resistor R1, it will enter in the resistor R2. Since current measures the rate of flow of charge, this means that the same current I flows through the R1 and R2. Means as this both connected at from both, and as these both the resistors are connected from both the end points, then the current that is flowing in one resistor go through another resistor also. Means same current is flowing in both the resistor, and by Ohm's law the potential difference across R1 is equals to V1 is equals to IR1, and potential difference across R2 is equals to V2 is equals to IR2. As according to Ohm's law we have formula that V is equals to IR, then the potential difference across both the resistor will be equal to potential difference V, which is equals to IR for IR1 for resistor R1 and IR2 for resistor R2, and the potential difference V across combination is V1 plus V2. Means if we take the combination of these two resistors V1 plus V2, then we get V is equals to V1 plus V2 is equals to I into R1 plus R2. Means as we have from potential difference the formula, we have V is equals to IR. Then if we take combination of the both the resistor V1 plus V2, will get IR1 plus IR2, and as I is common in both of these, we can take I out and multiply with whole R1 plus R2. So we'll get the V is equals to I into R1 plus R2, which is our equation 3.36. And this is as if the combination has an equivalent resistance Req, which is by Ohm's law is Req equals to V by I is equals to R1 plus R2. Means as this is as if the combination had equivalent resistor. Means as these are connected in parallel format, we assume that the combination has equivalent resistance in both resistors, and by Ohm's law it will be as Req is equals to V by I, as R is equals to V by I, which is equals to R1 plus R2. Means we are dividing V from formula, we have V by I, and also we have value of V is equals to IR1 and IR2. So when we substitute this value in the value of V, the I from denominator and numerator will be cut off, and we will get the Req, means equivalent resistor, is equals to R1 plus R2, which will be our equation 3.37. Now, if we have three resistors connected in a series format, then similarly, V will be equals to IR1 plus IR2 plus IR3. And as I is common in this, we can write this equation as I into R1 plus R2 plus R3, which is our equation 3.38. So for the three resistors in a series, we have equation V is equals to I into R1 plus R2 plus R3, which is equation 3.38. Now this is obviously can be extended to a series combination of any number of n resistors R1, R2 up to Rn. Means as I said previously, we can combine any number of resistors in a series combination, and the equivalent resistance Rq is considered as Req is equals to R1 plus R2 plus up to Rn. Means if we have taken n number of resistors, then our equivalent resistor will be in the format of equation 3.39. And now considered a parallel combination of two resistors as shown in 3.15, which you have already seen in previously. The charge that flows in at A from the left flows out partly through the R1 and partly through the R2. Means the charge which is flowing from this combination is flowing partly from resistor R1 and partly from resistor R2, and the currents I1 and I2 shown in figure are the rates of flow of charge at points indicated, and hence we have I is equals to I1 plus I2, which is our equation 3.40. Means the electric current that is flowing from first resistor and second resistor, and the electric current that is coming out from the combination of both the resistors, which is I1 and I2, is indicated as the flow as the rate of flow of charge, and from that we can say that I is equals to I1 plus I2. Means we get I from the combination of current from R1 and current from R2, which is I1 and I2. So we can say I is equals to I1 plus I2, which is our equation 3.40. Now the potential difference between point A and point B is given by Ohm's law applied to resistor R1, which is V is equals to I1 R1, which is our equation 3.41. And also Ohm's law applied to resistor R2 gives us V is equals to I2 R2, which is our equation 3.42. And we can say that and we from equation 3.40 we can say that I is equals to I1 plus I2, which is equals to, for according to Ohm's law, the formula for I is equals to V by R. And so if I1 plus I if we have I1, then we can say that we have V by R1, and for I2 we have V by R2. So we can say that I is equals to V by R1 plus V by R2, and is V is common in this both cases. We take V as common, and we can write that I is equals to V into 1 by R1 plus V 1 by R2. So we have the equation I is equals to V into 1 by R1 plus 1 by R2 as our equation for 3.43. Now, if the combination was replaced by an equivalent resistors Req, we would have by Ohm's law I is equals to V by Req, which is our equation 3.44. Means for our equivalent resistance, we have the formula Req is equals to V by I, and also Req for parallel we have for series we have Req is equals to R1 plus R2 up till then, but for parallel we have Req is equals to V by I, and which will be equal to R1 plus R2. So if the combination was replaced by equivalent resistance, then we will get equation as I is equals to V by R eq, means for instead of V by R1 and R2, we take V by R eq for parallel, and this is our equation 3.44, and hence we can say that 1 by R eq is equals to 1 by R1 plus 1 by R2, means as you have already seen previously, according to the equation 3.37, we have value of Req is equals to R1 plus R2. So we can also say that 1 by Req is equals to 1 by R1 plus 1 by R2, which is our equation 3.45. Now we can easily see how this is extended to 3 resistors in parallel. You can see figure 3.16 where 3 resistors are connected in a parallel format, and for these exactly as before, we can say that the current I, which is we are getting in output, is equals to I1 plus I2 plus I3, and this I1, I2 and I3 are the current flowing from particular resistor. So we can say I is equals to I1 plus I2 plus I3 for the case of 3 resistors in parallel, and this I is equals to I1 plus I2 plus I3 is our equation 3.46. And by applying Ohm's law to R1, R2 and R3, means all the 3 resistors, we get V is equals to I1 R1, V is equals to V1 is equals to I1 R1, V2 is equals to I2 R2, and V3 is equals to I3 R3, which is our equation 3.47. And so that we can say that I is equals to I1 plus I2 plus I3, which will be equal to V into 1 by R1 plus 1 by R2 plus 1 by R3, which is our equation 3.48. Again, the equivalent resistance that replaces the combination would be such that I is equals to V by Req, which is equation 3.49. It is same as equation 3.44. And hence we can say 1 by Req is equals to 1 by R1 plus 1 by R2 plus 1 by R3 for case of 3 resistor connected in parallel. And we can reason similarly for any number of resistors in parallel. The equivalent resistance of n resistor R1, R2 up to Rn is, means for n number of resistors that are connected in parallel, we can say equivalent resistance 1 by Req will be equals to 1 by R1 plus 1 by R2 up to 1 by Rn, which is our equation 3.51. These formula for equivalent resistances can be used to find out current and voltages in more complicated circuits. Mean if you want to find out the value of current and voltages in a complicated circuits, we can use the formula for equivalent resistances. Consider for example the circuit that is shown in figure 3.17. Here in the circuit you can see that there are 3 resistors R1, R2 and R3, and R2 and R3 are in parallel, and hence we can replace them by equivalent resistance Req23 between point B and C with 1 by Req23 is equals to 1 by R2 plus 1 by R3. Means here in figure you can see that in first on the top of the figure we have 2 resistors R1, R2 and R3 that are connected in a parallel format, and as you know that the formula for equivalent resistor 1 by Req is equals to 1 by R1 and R2, but here we have resistor R2 and R3 connected in parallel, so we'll have the formula for equivalent resistance 1 by Req 2 and 3 is equals to 1 by R2 plus 1 by R3. We are taking R2 and R3 because this R2 and R3 resistors are connected in parallel. If we have R1 and R2 connected in parallel, then we can take 1 by R1 plus 1 by R2, but here we have R2 and R3 connected in parallel, so here we are taking 1 by R2 plus 1 by R3, or we can say if we want the value for equivalent resistance Req for resistors 2 and 3, it will be equal to R2 into R3 divided by R2 plus R3. And the circuit now has R1 and Req23 in series. Now as we have found out the value of equivalent resistance of our parallel circuit R2 and R3, the circuit that is R1 is connected in series with this, so we can say we have series of R1 and Req23 in series, and hence their combination can be replaced by equivalent resistance with Req123 is equals to Req23 plus R1. As you have seen previously in our equation 3.39, we have said that if the resistors are connected in series, then the equivalent resistors will be addition of n number of resistors, say R1, R2 up to R1 plus R2 plus up to Rn. So Here we have R1 plus Req to 3. So for equivalent resistance in this series, we have equivalent resistance Req1 to 3 is equals to R1 plus Req to 3, which is our equation 3.53. And if the voltage between A and C is V, then the current I is given by I is equals to V by R. As you know the formula previously, I is equals to V by R Eq of 1 to 3 is equals to V divided by R1 plus in bracket R2 into R3 divided by R2 plus R3, which will be equal to V into R2 plus R3 divided by R1 into R2 plus R1 into R3 plus R2 into R3, which is our equation 3.54. So this was our topic 3.10, combination of resistors in series and parallel. Now we will move to our next topic, which is 3.11, cells, EMF and internal resistance. We have already mentioned that a simple device to maintain a steady current in an electric circuit is electrolytic cell. Means it is mentioned previously that a simple device that is used to maintain a steady current in an electric circuit is called electrolytic cell. Basically, a cell has two electrodes which are called positive P and the negative N, as shown in figure 3.18a and B. Means in figure 3.18 you can see that there is a cell which has two electrodes. First one is positive and second one is negative, and they are immersed in an electrolytic solution. Dipped in this solution, the electrodes exchange charges with electrolyte. Means when this uh, positive and negative electrodes are dipped in the solution, these electrodes exchange their charges with the electrolyte, and the positive electrode has a potential difference V plus. V plus means the value is greater than 0 because between itself and the electrolytic solution immediately adjacent to its mark A in the figure. As you can see in the figure, the potential difference V plus is marked marked as A in the figure. Similarly, for the negative electrode develops a negative potential which is minus V minus, and V minus is greater than or equal to 0. Relative to the electrolyte, the adjacent to it is marked as B in the figure. Means this negative electrode is marked as B in the figure, as you can see. When there is no current, the electrolyte has the same potential throughout the circuit, so that the potential difference between P and N is V plus minus minus V minus, which is equals to V plus plus V minus. Means when there is no current flowing inside the circuit, the potential difference will be same throughout the circuit, and the potential difference will be given as V plus plus V minus, and this difference is called the electromotive force EMF of the cell, and it is denoted by epsilon symbol. Thus we can say that epsilon is equals to V plus plus V minus, which is greater than 0, which is our equation 3.55. Means this potential difference that we got is called electromotive force, and we can say that it is E is equals to epsilon is equals to V plus plus V minus, and its value is greater than 0, which is equation 3.55. Note that epsilon is actually a potential difference and not a force. The name EMF, however, is used because of its historical reasons and was given at a time when the phenomena was not understood properly. Means this name was given when the phenomena was not understood properly. It is just a potential difference and not a force. To understand the significance of this epsilon, consider a resistor R that is connected across the cell shown in figure 3.18. A current I flows across R from C to D. Means we have to consider a resistor R that is connected with the cell, and the current is flowing from point C to D across the resistor R. As explained before, a steady current is maintained because the current flow from negative to positive through the electrolyte. Clearly across the electrolyte, the same current flows through electrolyte but from N to P, whereas through R it flows from P to N. Means when R is not there, the current flows from N to P, but as R is there, then the current is flowing from P to N, and the electrolyte through which a current flows has a finite resistance R called the internal resistance. Consider the first situation where R is infinite, so that I is equals to V by R, which will be equal to 0, where V is potential difference and P and N, between P and N, between positive and negative electrode. Now V is equals to potential difference between P and A plus potential difference between A and B plus potential difference between B and N, means for this case we'll have the potential difference V is equals to potential difference between P and A, between A and B, and between B and N, and which will be equals to our epsilon, or we can say our electromotive force EMF, which is our equation 3.56. Thus, EMF epsilon is the potential difference between the positive and negative electrode in an open circuit, that is, when no current is flowing through the cell. If, however, R is finite, I is not 0. Means if we have the value of resistor R is finite, then our current will be non-zero, and in that case the potential difference between P and N will be V is equals to V plus V minus I into R, which is equals to epsilon minus IR. As we have seen in our equation 3.55, we have value of V plus V minus as epsilon, so we can say V is equals to epsilon minus IR, which is our equation 3.57. Note that the negative sign in the expression IR for potential difference between A and B, this is because the current flows I from B to A in the electrolyte, means the current is flowing from negative side to positive side, and hence we are using the negative side in the expression IR. In practical calculations, the internal resistances of the cell in the circuit may be neglected when current I is such that epsilon is double greater than IR, means right shifted to IR. The actual values of internal resistance of cells vary from cell to cell, means the internal resistor of each and every cell will be different from another. And the internal resistance of dry cell, however, is much higher than the common electrolytic cells. We also observe that since V is potential difference across the R, we have Ohm's law is equals to V is equals to IR, which is equation 3.58, and combining equation 3.57 and 3.58, we get value as IR is equals to E minus IR. And if we want to have the value of our current I, then we have to take the resistance R in right hand side, and if we take that in right hand side, we'll get it in the division, and we'll get the value of our I is equals to E divided by R plus small r, which is our equation 3.59. So our equation, combining equation 3.57 and 3.58, will get I is equals to epsilon divided by R plus small r, and the maximum current that can be drawn from the cell is, for R is equals to 0, and it is I max is equals to E by R. However, in most of the cells, the maximum allowed current is much lower than this to prevent permanent damage to the cell. Let us see an example, example 3.5, according to which a network of resistor is connected to a 16V battery with internal resistance of 1 ohm, as shown in figure 3.19. We have to calculate three things. A. Compute the equivalent resistance of the network. B. Obtain the current in each resistor. And C. Obtain the voltage drops VA, B, VBC and VCD, means we have to compute the equivalent resistance in the network. We have to obtain the current in each and every resistor, and also we have to obtain the voltage drops in VAB, VBC and VCD. So let's look at our solution. For our solution of A, we have to compute the equivalence resistance of the whole network. So the network is simple series and parallel combination of resistor, means as you have seen the figure, you can see that in our network we have combination of parallel and series resistors. And first, the two 4 ohm resistor in a parallel are equivalent to a resistor, means first we will calculate the equivalent resistance for the two parallel connections of which is of 4 ohm, and which will be equals to 4 into 4 divided by 4 plus 4 ohm, which is equals to 2 ohm. So our equivalent resistors from the formula of equivalent resistance for parallel combination, we can get the equivalent resistance for two resistors as 4 into 4 divided by 4 plus 4, which is equals to 16 by 8 ohm, which is equals to 2 ohm. In the same way, the 12 ohm and 6 ohm resistors in a parallel are equivalent to the resistors of 12 into 6 divided by 12 plus 6, which is equals to 4 ohm. Means we have also another connection of 12 into 6 ohm, and the equivalent resistance for that combination will be 4 ohm. Now the equivalent resistance R of the network is obtained by combining these resistors 2 ohm and 4 ohm with 1 ohm in series. Means remember that these two parallel connections are also connected in series with the 1 ohm resistors, and by combining the equivalent resistance of these two resistors with the resistor of 1 ohm, we'll get the value of R is equals to 2 ohm plus 4 ohm plus 1 ohm is equals to 7 ohm. So our equivalent resistor for whole the network will be 7 ohm. This is our solution A. Now we will look at our solution B. For solution B, we have to obtain the current in each and every resistor. So the total current I in the circuit is I is equals to E plus R plus small r, which was our equation 3.59. In order to get our total current in the resistor, we have formula as I is equals to E divided by R plus R. Now our epsilon value is 16V, which is given in the question, and our R, which is equivalent resistance, is 7 plus 1 ohm is for our series connection. So 16V divided by 7 plus 1 ohm is 16 divided by 8, which will be our current 2A. Now consider the resistor between A and B. If I1 is the current in one of the 4 ohm resistor and I2 be the current in another one, then I1 into 4 will be equal to I2 into 4, and that is I1 is equals to I2. As there is 4 on both hands side, it will be cut out, so we'll have I1 is equals to I2, which is otherwise obvious from symmetry of 2 arms. But I1 plus I2 is equals to I, which equals to 2A, and thus I1 is equals to I2 is equals to 1A. That is current in each 4 ohm resistors is 1A. Current in 1 ohm resistor between B and C would be 2A. Now consider the resistances between C and D. If I3 is current in 12 ohm resistor and I4 is in 6 ohm resistor, then I3 into 12 is equals to I4 into 6. That is I4 is equals to 2 times I3, but I3 plus I4 is equals to I is equals to 2A, and thus we have I3 is equals to 2 by 3A and I4 is equals to 4 by 3A. So our current, all over current is 2A, and current for the in the resistor R3 and R4 is I3 is equals to 2 by 3 and I4 is equals to 4 by 3A. So this is our solution for our B. Now we will move to our solution C. For our C, we have to obtain the voltage drops in VAB, VBC and VCD. So, the voltage drop across AB is VAB, which is equals to I1 into 4, which is equals to 1A into 4 ohm, which is equals to 4V. Now, this can also be obtained by multiplying the total current between A and B by equivalent resistance between A and B. This is V, A and B is equals to 2A into 2 ohm, means we are multiplying here the total current and total resistance of A and B, which gives us 4V. The voltage drop across BC is equals to 2A into 1 ohm, which is equals to 2V. Finally, the voltage drops across CD is VCD is equals to 12 ohm into I3 equals to 12 ohm into 2 by 3A, which is equals to 8V. And this can be alternately be obtained by multiplying total current across C and D by the equivalent resistance between C and D, that is V C and D is equals to 2A into 4 ohm, which is equals to 8V. Note that the total voltage drop across AD is 4V plus 2V plus 8V, which is equals to 14V, and thus the terminal voltage of battery is 14V while its electromotive force is 16V. The loss of voltage here is 2V is accounted for by the internal resistance of 1 ohm of battery. 2A into 1 ohm is equals to 2V. So this is our solution for C. So this was our topic, cells, EMF and internal resistance. Now we will move to our next topic, topic 3.12, which is cells in series and in parallel. Like resistors, we can also combine the cells in an electric circuit, and like resistors, one can, for calculating currents and voltages in a circuit, replace a combination of cells by equivalent cell. Consider first two cells in series, figure 3.20 means two cells are connected in a series format when one terminal of two cells is joined together, leaving the other terminal in either cell free. Epsilon 1 and epsilon 2 means electromotive force 1 and electromotive force 2 are EMFs of two cells R1 and R2. Our cells, we have represented them as R1 and R2. Their internal resistance, R1 and R2 is their internal resistance. Sorry, there's a mistake. Our R1 and R2 is a internal resistance respectively for both the cells A and B. Now let VA, VB and VC be the potential at points A, B and C shown in figure 3.20. Then VA minus VB is potential difference between positive and negative terminals of the first cell. We have already calculated in equation 3.57, and hence VAB is equals to VA minus VB, which is equals to E1 minus IR1, which is our equation 3.60. Similarly, for the potential difference VB and VC, we have VBC is equals to VB minus VC, which is equals to epsilon 2 minus IR2, which is our equation 3.61. And hence the potential difference between the terminals A and C of the combination is VAC is equals to VA minus VC, which is equals to VA minus VB plus VB minus VC, which is equals to epsilon 1 plus epsilon 2 minus I into R1 plus R2, which is our equation 3.62. And if we wish to replace the combination by a single cell between A and C of EMFs epsilon EQ and internal resistance Req, we would have VAC is equals to equivalent epsilon minus equivalent internal resistance EQ minus IREQ, which is our equation 3.63. Comparing the last two equation means equation 3.63 and 3.62, if we compare this both equation, we get epsilon EQ is equals to E1 plus E2 and internal resistance Req is equals to R1 plus R2. Here our E1 plus EQ is equals to E1 plus E2 is our equation 3.64, and Req is equals to R1 plus R2 is our equation 3.65. In figure 3.20, we have connected the negative electrode of the first cell to the positive electrode of the second cell. If instead we connect the two negative electrodes of both cells with each other, equation 3.61 would change to VBC is equals to minus E2 minus IR2, and will get epsilon equivalent is means equivalent electromotive force is equals to E1 minus E2, where value of E1 will be greater than E2, which is our equation 3.66. And we got this equation 3.66 if we connect the negative ends of both the cells with each other. The rule for series combination clearly can be extended to any number of cells. First is the equivalent EMF of a series combination of n cells is just the sum of their individual EMFs, and second is the equivalent internal resistance of a series combination of n cells is just the sum of their internal resistances. And this is so when the current leaves each cell from the positive electrode. If in the combination the current leaves any cell from negative electrode, the EMF of the cell enters the expression of equivalent EMF with a negative sign as shown in equation 3.66. Next, consider a parallel combination of cells shown in figure 3.21. Here I1 and R2 are the current that are leaving the positive electrodes of the cell. At point B1, I1 and I2 flow in, whereas the current I flows out. Means the current I1 and I2 flow in the cell, and the current that we got in output is our current I. Since as much charge flows is as out. We have I is equals to I1 plus I2 as equation 3.67, and let VB1 and VB2 be the potential differences at B1 and B2 respectively. Then, considering the first cell, the potential difference across its terminal is VB1 minus VB2. Means in case of the first cell, which is B1, we have potential difference across its terminal as VB1 minus VB2, and hence from equation 3.57 we have V is equivalent to V into B1 minus V into B2, which is equal to epsilon 1 minus I1 R1, which is our equation 3.68. Points B1 and B2 are connected exactly similarly to the second cell, and hence considering the second cell we also have V equivalent to V into B1 minus V into B2 is equals to epsilon 2 minus R2 I2 R2, which is our equation 3.69. Now combining the last three equation, which was our equation 3.67, 3.68 and 3.69, we get I is equals to I1 plus I2, which is equals to, for I1 we have value epsilon minus V divided by R1, for I2 we have value epsilon 2 minus V divided by R2. So we'll have I is equals to epsilon 1 minus V divided by R1 plus epsilon 2 minus V divided by R2, which will be equals to epsilon 1 by R1 plus epsilon 2 by R2 minus V into 1 by R1 plus 1 by R2, which is our equation 3.70, and hence V is given by V is equals to E1 R2 plus E2 R1 divided by R1 plus R2 minus I into R1 R2 divided by R1 plus R2, which is our equation 3.71. If we want to replace the combination by a single cell between B1 and B2 of electromotive force EEQ and internal resistance REQ, we would have V is equals to EEQ minus IREQ, which is our equation 3.72. We take this if we want the whole combination to be replaced by a single cell, and the last two equations should be same, and hence EEQ is equals to E1 R2 plus E2 R1 divided by R1 plus R2 is equation 3.73, and REQ is equals to R1 R2 by R1 plus R2, which is our equation 3.74. We can put these equations in a simpler way. 1 by REQ is equals to 1 by R1 plus 1 by R2, which is our equation 3.75, and EEQ divided by REQ is equals to E1 divided by R1 plus E2 divided by R2, means which is our equation 3.76. In this equation we have put or represented our equations in a simpler way. In figure 3.21 we have joined the positive terminals together and similarly two negative ones, so that the current I1 I2 flow out of positive terminal if negative terminal of second is connected to positive terminal of first. Equation 3.75 and equation 3.76 would still be valid with epsilon 2 tending to minus epsilon 2. Equation 3.71 and 3.76 can be extended easily, and if there are n number of cells, EMF of E1 up to En and of internal resistance R1 up to Rn respectively connected in parallel, the combination is equivalent to a single cell of EMF EEQ and internal resistance REQ, such that 1 by REQ is equal to 1 by R1 plus up to 1 by Rn if we have taken n number of cells, which is our equation 3.77, and EEQ divided by REQ is equals to E1 by R1 plus up to En divided by Rn, which is our equation 3.78. These equations are in case if we have taken n number of cells in our whole network. So these were our three topics that we have discussed, which were, first one was 3.10 combination of resistors, series and parallel. Second was 3.11 cells, EMFs and internal resistance, and the last one was 3.12 cells in series and in parallel. So this is it for today. Our next topic we will cover in our next session. Thank you.